Okay, I think we're all set. Welcome everybody. I'm Dan Carnevale. I'm responsible for our experience centers. How many of you have been to the Houston Experience Center? Anyone? Couple? Only a couple. So it's basically Disney. It's electrical Disneyland. So I would definitely suggest that you should go to the Houston Experience Center if you're there. And I'm out of Pittsburgh. We also have one in Pittsburgh. It's basically everything that you can imagine from electrical designs, like lots of arc flash solutions, lots of applications with panel board, switchboard, switchgear, and it's real and it's working environments. So what's our experience centers? Basically, the experience centers are full-scale equipment, live equipment, and somebody to show you around and talk about, you know, how things work. And so you saw the Power Up program that we're talking about here. So for young consulting engineers or new people into the industry, we have these programs to talk about. You remember when you were in school and you got out of school and you knew that a transformer was two squiggly lines on a piece of paper? That's what we all learned, right? But we know they don't really look like that in real life. But unfortunately, like, we brought in a bunch of new hires to Eaton one time. We put like 20 of them in a room. And we said, okay, now point to a transformer. And they looked at us like, you know, like, but if we drew the squiggly lines on a piece of paper, that made more sense. So as engineers, a lot of times we learn stuff on paper, okay? What I'm going to talk to you about today in the terms of harmonics is something a little different than what we learn about in school. We learn that voltage equals current times resistance or impedance, right? That's Ohm's law. And way back in school, we also learned about constant current sources. How many times in your life have you used a constant current source for any kind of calculations or anything? Never, right? This is the one place where constant current sources make sense, and I'm going to explain why. But basically, who cares about harmonics, right? If you're a designer or a consultant, why do you care? If you're an operator, if you're a person running a facility, why do you care? If you're a salesperson or a representative that's putting equipment in, why do you care? First of all, what are harmonics? Where do harmonics come from? When we say harmonics come from what? How would you answer that? Nonlinear loads. I heard nonlinear loads. What's a nonlinear load? Are there any nonlinear loads in this room? Actually, yeah, I heard all. Are there any linear loads in this room? Probably not. If we had incandescent lights, maybe, but most of these are probably either LED or fluorescent or some sort of lights. Projector, the computer, all those are nonlinear loads. So nonlinear loads produce harmonic currents, and they send them out onto the system, and then what happens? And the currents flow through impedance, and what happens when current flows through impedance? It produces what? Voltage. And then we screw up our voltage. So we're going to talk about who cares about harmonics and why do we care, okay? But harmonics, my life has been basically power quality. There's 4 major power quality things, right? Grounding, harmonics, transients, and voltage variations. These are 5 different things that fall into those categories, but they're all a little bit different. So they're not all the same, but what we're going to focus on is one part of power quality, and that's harmonics. So this is what an outage would be, right? Voltage goes to 0. Now, if I call the utility and tell them I had an outage, what might they say? Nah, you didn't have an outage. You had a what? You had a momentary. If they don't have to roll a truck, you didn't have an outage. It was just a short-term interruption, okay? But that's a story for a different day, okay? What's that? That's a surge or a transient. That's a single pulse of voltage usually, maybe a lightning strike, maybe a capacitor ring wave, something like that. And that can cause all kinds of problems, but that's a little different than what we're talking about today. Can that trip a variable frequency drive? If it's a capacitor ring wave, yeah. You get a DC bus overvoltage, it might trip on overvoltage. But again, it's slightly different than what we're talking about today. What's a sag or a swell? A sag is where the voltage goes down for a little bit, and a swell is where the voltage goes up for a little bit, usually less than a couple seconds. What's a longer sag or a longer swell? A longer sag is called an undervoltage, a longer swell is called an overvoltage. Okay, so again, those are all power quality terms that we're not going to talk about today, so I'm setting sort of the details of what we are going to talk about and that's harmonics. So it's distortion in the wave shape, okay, that can cause problems, and it's either current distortion or voltage distortion. We'll talk about where all that comes from, okay? Now, you see the picture here on your left. That's a linear load. Current looks like the voltage. Okay, this is the current, that's the voltage. Current looks like the voltage, and it's reflective of the voltage. So it looks very much like it. This is a nonlinear load. The current doesn't look like the voltage. And by the way, that current then screws up the voltage. So now we have two problems. So let me ask you this. If I told you, is anybody working with electric vehicle charging right now? Okay, some people. If I told you of these two waveforms, which of those is going to look most like electric vehicle charging? You would assume that one, right? You want some good news? Looks like this. Although it's even in phase, this is a lagging current, right? So voltage crosses, then current crosses. But I've tested probably 15 different electric vehicles, and the chargers on those vehicles, the current distortion is less than 10%, most of them less than 5%. So it almost looks very linear, which is really good news for all of us, because honestly, that could be another nightmare, okay? But what kind of current is that one, that double hump current? Where does that come from? VFDs. And what type of VFDs, to give you another question, 6 poles, 12 poles, 24 poles? 6 poles. And what are the harmonics associated with 6 pulse drives? 5 and 7. So you took 6 plus or minus 1, and then 2 times that, 12 plus or minus 1, 11th and 13th. We'll come to that. But harmonics are predictable. That's the good thing. We know they're predictable, and they're characteristic of certain specific loads. So this projector has specific harmonics, drives have specific harmonics, other rectifiers have specific harmonics, and we can predict that, and then we can decide what to do with it, okay? But it seems really complicated, doesn't it? So everybody's always said, oh, harmonics are really complicated, we need to worry about it. It's not really that complicated. What it is it goes back to Ohm's law. Voltage equals current times impedance, okay? And more specifically, voltage distortion equals current distortion times the harmonic impedance. Does impedance change? Let me ask you this. If you have a resistor, does the impedance change? Not really. Maybe a little bit with temperature, but not really. Does an inductor, does the impedance change? It does if you have what? If you have 60 hertz, it's 2 pi times F times the inductance, right? But what's the F, what's the frequency of the harmonics? It's another frequency that's typically higher, right? So if it's the 5th harmonic, it's 5 times 60 or 300 hertz. So the impedance does change as we go up in frequency. So that's a variable. The harmonic current, we said, comes from the nonlinear loads. So does that change? Yeah. If I have a factory or I have a conveyor system and I don't have any VFDs, and all of a sudden I put VFDs on all my motors, I've added much more current distortion. So based on this one and this one, that one then becomes bigger or worse, you could say, okay? So as you start off, you add more and more harmonic current loads. The systems are built for 60 hertz. What happens is the current distortion starts to cause heating. And then, oh, by the way, it starts to add more voltage distortion. And the bigger the harmonic current, the bigger the voltage distortion, very much proportional. And then what happens is, guess what? We switch from utility to generator. Who knows what a standard impedance is for a transformer if you do an arc flash study or a short circuit study? 5.5 to 6%, okay? What's the standard impedance, XD double prime, for a generator? What? 12, yeah, so it could be 12 to 20%, right? So let's say it's 18%. So if it's 6% on utility and 18%, now this impedance here changes not only from the inductance changing according to the frequency, but it changes because I'm going from utility to generator source. So now I've got 3 times as much impedance when I'm running on a generator with my same harmonic current. So guess what happens to my voltage? My source impedance changes, my voltage distortion goes crazy, right? So what do people do? Oh, I got a bad generator. Got to test my generator. So they roll in what? A load bank. What's a load bank? It's a resistor. Is that a linear or nonlinear load? It's a linear load. Voltage distortion equals current distortion times harmonic impedance. So no matter what this is, if that's 0, it doesn't matter, okay? So you're never going to see this with a load bank, are you? And this is one of those things as a designer you have to think about, right? So now which came first? Voltage distortion or current distortion? What did we just talk about? What causes what? Does voltage distortion start or current distortion start? Current, right? So this is where that constant current source comes into play. If I have a constant current source and I'm pushing that current through my system, however much current distortion I push through my system, that's going to dictate how much voltage distortion I have. What do you think are some of the issues with current distortion? I'm pushing extra current through my system. What's a natural thing for extra current to happen? Heat. Then I screw up my voltage. What's one of the things that's going to happen if I screw up my voltage? Yeah, you're going to have misoperation. Other equipment's not going to like that because it's expecting a certain voltage, and now you're going to give it a crappy voltage that it's not going to like. So depending on if you increase your source impedance or if you have more harmonic load, you're going to get more distortion. What do you think about that voltage waveform? Would you like to have that in one of your designs in your facility? That's actually, so I'm not going to have time to tell the story of the bad noise and the evil noise, but this was off an oil platform in the Gulf of Mexico. I actually went out, they dropped me off in a helicopter. They're like, fix that and we'll be back to pick you up when you fix it. So we have this in one of our videos. I'm going to talk a lot about videos later, but we have about 200 videos. 50 of them are on harmonics only. So you want to talk about harmonics? I love to talk about harmonics. You can listen to the videos. They're like 5 to 10 minutes, but they talk about all different types of things. We also have power quality videos. One of them is on case studies, and that is in one of the case studies. But the point of this is, we always say harmonics are not a problem unless they're a problem. Seems a little silly, right? But going back to who are you and why do you care about harmonics? They're not a problem unless they're creating other issues. What are the issues? Heating or misoperation. Are harmonics the new normal? Absolutely. You're going to have harmonics. You're not going to get around having harmonics. So how you deal with them and what you worry about is what's important. We talked about the Power Up program at our Experience Center. We get new consultants in. We always tell the consultants, we say, look, if you design the cheapest, crappiest system, you probably could save a lot of money for your first customer, but then in 6 months you won't have a job because they're not going to like your design because it's going to fail and it's, whatever, right? On the other end, if you design the most expensive, bulletproof, 100% going to work every time, in 6 months you're not going to have a job because nobody wants to pay the most expensive thing every single time, right? Your job as designers is to balance. What's the good, better, best version? Harmonics are exactly that. Sometimes the best solution is, believe it or not, doing nothing because harmonics are the new normal. If I don't have a problem with that waveform, I don't care. But in a lot of cases, if I have things like multiple zero crossings, yeah, it's probably going to be a problem. Transfer switches don't like that. Digital clocks, like on the oil platform, they run really fast when you see something like that. So in the paper, okay, in the paper we talk about basically symptoms, sources, and solutions of harmonics, okay? And then we talk about, the IEEE standard. What's the IEEE standard that you have to, that governs harmonics? 519, okay? We'll talk about that in a minute, but that's in there as well. And then we have some tables at the very end of the paper that basically talk about, cost differential and stuff. So if I'm comparing a line reactor to an active harmonic filter, how does that look, But what's the cost benefit of it? And how do they compare? As you look at the general sources of harmonics, it's really anything that goes from AC to DC. So, phone chargers, every single thing that's electronic is probably going to produce harmonics, so we have to deal with that. LED lights are LED lights, although they're a lot less load today, but variable frequency drives are probably the most significant one today. As far as deciding which characteristic harmonics you have, we talked about 6 pulse drives. So here's the equation right down here. If you have a 6 pulse drives, it's n, which is an integer, 1, 2, 3, 4, 5, 6, times p, number of pulses, plus or minus 1. So for a 6 pulse drive, 6 plus or minus 1, 12 plus or minus 1, 18. If I have a 24 pulse drive, it's 24 plus or minus 1. And as the harmonics go up in order, they go down in magnitude. So a 24 pulse drive has a lot less harmonics than a 6 pulse drive. Fifth harmonic for a 6 pulse drive is here. The 24 pulse drive has 23rd and 25th harmonic that are way lower. So it looks more linear, more like a resistive load, okay? And then you have things like, switch mode power supplies or computer power supplies. It has all the odd harmonics, or LED lighting. What do you notice about these last two? Even harmonic. So odd harmonics are typical. Even harmonics create asymmetry. And if you see me start to sweat up here and act a little weird, it's because I'm used to like drawing on the board and acting like I always want to like refer to like drawing on stuff. So if you watch some of the videos, I'll talk somewhat through that. But even harmonics, if you looked at the top half of the waveform and the bottom half of the waveform, even harmonics are not the same. Odd harmonics, the top half of the waveform and the bottom half are exactly the same or symmetrical, okay? So even harmonics are an indication of something different than normal. When you energize a transformer and you hear that dong, it doesn't last forever, does it? It's only there for a little bit. Arcing devices like steel mills, arc furnaces, stuff like that. That can be short term, but it's not usually consistent for a long period of time. So how do you know you have a problem? Okay, we're talking about solutions. So a solution implies you have a problem. Well, we talked already about it. Current harmonics, which come from the loads and push back into the system. That's our constant current source. Let's say I have a VFD, and it's a 30 horsepower drive, and it produces 10 amps of fifth harmonic current. Where does that 10 amps go? It flows out on one of the conductors. How many phases is a drive, typically? 3 phases, right? So it flows out on the conductor. Does it go to ground? Nope. It goes out on A, back on B and C. Just like normal current going into the drive, except it goes the other way, okay? So one really important thing that they forgot to tell us when we're in college is that current flows in a loop. I wish they told me that current flowed in a loop. It made so much more sense once I discovered that. It's such a simple thing. But think about it. Current flows in a loop. It doesn't go over there and stop. So if current flows in a loop, that means it goes all the way over there somewhere and all the way back here, because it can't stop until it gets back. Okay? You want to hear what one of the guys in my college, like senior year in college, he asked my college professor, he goes, what do they do to the end of transmission lines? Do they just tie them to ground? And he goes, what did you say? He's like the 70-year-old crusty guy who's like really peed off all the time. He goes, what are you saying? And he goes, no. He goes, oh, forget it. Because he realized voltage can sit there all day long. Voltage is a potential. It's a difference, right? But if you have current, it has to flow out and back. So again, I wish they told us that because it makes so much more sense. Things like current transformers and potential transformers and things like that. If you understand that, you understand harmonics. So current harmonics flow out onto the system and they flow back on the other conductors. Third harmonics flow out on the system and they flow back where? On the neutrals, and they add up on the neutrals. And so there's other issues associated with that. But here's an example of a transformer getting really hot because of harmonics. Anybody know what this is? Capacitor. That's the outside of the capacitor, that's the inside of the capacitor. If you see the inside of the capacitor, that's probably bad. All right? If you blow the fuses, that's probably bad. That's called resonance. We don't like resonance. Resonance is bad. All right? What other symptoms or issues do you have if you have harmonics? You could have audible noise. If you walk up to a transformer, it can make buzzing and noise like that. You could have other issues like that, right? You could have things turning on and off when you don't want them to. One of the examples I like to give is I was in an auto plant and they were doing welding. And they were doing welding based on 20 cycle welds, electrical cycles. So a third of a second, 20 electrical cycles. How do they tell how long it is? 0 crossing, 0 crossing, 0 crossing. That's 1 cycle, okay? Well, what if there's a lot of notching going on the waveform? Zero crossing, like multiple. So they were doing, instead of 20 cycle welds, they were doing 8 cycle welds. And the welds were falling apart. Tailgates were falling off of minivans. But they didn't know that until like months later, and they get a recall, and they're like, what the heck's going on? Well, the voltage distortion was causing the welding equipment not to operate properly, but nobody put that together and looked at it as a power quality problem. They thought it was just, you know, a bad welder. This is the kind of stuff you can see, though. Now, we show sort of this doctor analogy, right? So if you go to the doctor and you say, hey, doc, I got a problem, do they go like this? Do they go, let's try brain surgery. If that doesn't work, we can put a cast on your leg. If that doesn't work, we'll give you a shot. Do they do that? Let's hope not, right? Maybe get a new doctor. But if they do that, what are they going to ask you first? The symptoms. This is why it's really important. If you have voltage drops, sags, and you're dropping out drives based on voltage sags, that's not harmonics. If you have a transformer overheating, that's not sags. That's why I related everything back at the very beginning of this to which power quality problem were we talking about. So the symptoms here tell you what the problem is so you know how to fix it. Then there's other economic considerations, and that really relates to if you're doing power factor correction and you're blowing up capacitors, or maybe you have a power factor penalty. Maybe you put in harmonic filters. Is a harmonic filter a power factor correction device? Believe it or not, a harmonic filter is primarily a power factor correction device that you don't want to blow up because you avoid resonance. And secondly, it offers harmonic filtering. It has a primary benefit of power factor correction in almost all cases. I wouldn't say there's always, right? But the secondary benefit. And the more you detune it, you ever hear of detuned harmonic filters? 4.7th, 4.2nd, 4.1st. The more you detune it, the more you want it to be power factor only, as opposed to getting close to the harmonic where you want to try to get rid of the harmonic. So there's a lot of little things that go along with that you have to understand when you're applying things. But even previously, remember when we said, let's say the impedance of a generator is 18%? How can you make that impedance smaller? What did they used to do with all data centers? They would double the size of the generator. It wasn't because they needed 2,000 kilowatts. They needed 1,000 kilowatts. But what were they effectively doing? They were cutting the impedance in half. So you basically bought this big generator, and the only reason you bought the big generator was so you could get the impedance in half. Now we have active front-end UPSs, and they look almost linear, so they don't have that problem anymore, okay? So IEEE 519 2022 is the latest standard, believe it or not. They just came out with a new one last year, and they just included a few different things in there with inverters and stuff. But previous to that, there was an update in 2014. Does anybody know when the update before that was? 1992. Forever they kept saying, we're going to update, we're going to update. So they went from this 1992 standard, it was almost like, it was almost 100 pages, and they reduced it down to like 17. They made it much more concise in 2014, which is good news. But anyway, when we talk about harmonics, we could talk about internal versus external sources. And if we're talking about like us versus our neighbor, that's important to know. There's a thing they say in the standard called a point of common coupling. Okay, the point of common coupling is where me and my neighbor come together, and if I'm sending that current out onto the system, screwing up the voltage on the utility system, who's going to take responsibility for that? Well, the utility is going to enforce and say, you are. You're going to do that because it's your fault. You're screwing up your neighbor. All right? But sometimes you have to look at the data. And in this case, if you look at this, remember we said current distortion causes voltage distortion? Right now, my plant's shut down. I have no load, but I have 4% voltage distortion. So what does that tell you? Where's that coming from? It's coming from the source. It's coming from maybe somewhere else, the neighbors. Maybe they're creating the voltage distortion, because just because I go from 4% to say 5 or 6% doesn't mean I cross this magic threshold and all of a sudden my stuff's going to fall apart. But if the utility comes back to me and says, hey, you've exceeded this limit that we've imposed, well, you should look at, am I causing it or is the neighbor causing it? Has anybody modeled in SKM or any other program harmonics at all? So so what you do is you put it in as a constant current source, and you do multiple load flows, at every frequency, 60 hertz, 300 hertz, 420 hertz, and it tells you where the currents flow, how much voltage distortion you get, and this kind of stuff becomes evident. So here's some of the stuff out of the standard, comparing again the 92 standard to the 2014 standard. And again, you can see the bottom line there is it really reduced the scope of it, because there was a whole bunch of educational stuff in there, and they just really got down to the main points of voltage distortion tables and current distortion tables. And it's much more, actually they freed up a little bit on the voltage distortion. They allow you to get a little bit more, and that's really just based on experience. What they found is people can live with more voltage distortion than they thought they could, okay? But here's a comparison of in the 2014 table, and this is the same in the 2022 table, by the way. But you can have 8% total distortion, and then the individual ones can be a certain amount as well, but they're lower. And we'll talk about how to calculate total harmonic distortion. So that's what this is. If I take this wave, any waveform, current or voltage, and I go from here to here, that's one electrical cycle of 60 hertz. Then I break that down with math called FFT, fast Fourier transform, and I get a 60 hertz part, and I get a 180 hertz part, 300 hertz, so third harmonic, fifth harmonic, seventh harmonic, 11th harmonic, 13th harmonic, okay? Now let's say, just for simplicity of math, let's say the 60 hertz part is 100 amps. So 100% of 100 amps is 100 amps, so that's good. What's 20% of 100 amps? 20 amps. So I have 100 amps, 20 amps, 12 amps, 4 amps. So if I square all those and divide by 100, I get 23.8%, okay? But I want to tell you, be very careful when you're doing percent distortion, because what can happen is you can end up with a number like that, and then overnight you might drop your harmonics just a little bit, but let's say your 60 hertz increases a lot. Let's say you have a bunch of motors that are across the line. Let's say this number doubles. All of a sudden your THD goes way down, even though you might have the same amount of harmonic current. So it's really more about the amps of harmonic, not about the percentages. And so in the IEEE standard, they focus on what they call TDD, total demand distortion. And that's really just focused on this number here, which is the demand. And if you look at an actual example, this is a 18 pulse drive. Look at the actual amps of harmonic current. 8.2 amps, 9.2, 10.1, 10.8. They increase as I add load, okay? Not nearly dramatically as the fundamental increases. The fundamental kind of is proportional to the actual load. It increases pretty significantly. So if you look at the THD at a light load, you have 26% distortion. You say, holy cow, that's horrible, right? But really, you have less amps of harmonic there than at 60 hertz where you have 5.9%, okay? Which is the worst case. This is the worst case. I have more amps of harmonic distortion. So if you use TDD, you divide by the demand load, which is the worst case scenario, then I go pretty much increasing, and it feels better as far as what's increasing with my load. The other thing about this is, you might say, well, I want my drive to have less than 5 or 6% distortion. You go, well, okay, it is at 60 hertz, but why do you buy a drive? Do you buy a drive to run it at 60 hertz? No. If you do, I'll sell you a whole bunch of other stuff, because that's a really bad waste of money. Run a drive at less than 60 hertz to save, or you run it at less and more to change frequency to avoid, or to control the speed, right? Here's the current distortion table, and again, the important thing here is that TDD value, and it increases with what? I short circuit over I load. So if the load is the same, I have a 30 horsepower load, and I put it on a 30 kVA transformer. That ratio of 30 kVA transformer to my load, pretty low. Meaning I'm loading up that transformer. If I put that same 30 horsepower load on a 3 MVA transformer, do I probably care at all? No. In other words, if I add a 30 horsepower drive on a 3 MVA transformer, am I going to go do a $20,000 harmonic study? Again, probably not worth it, okay? So short circuit overload is important, meaning how much am I loading down the system, because what does that really imply? It implies how much I'm screwing up my voltage, okay? People always get caught up in that number right here. They go, well, 20% distortion. I have 40% distortion. My building's going to burn down, okay? Well, let's, again, think about it in real amps, all right? If I had 20% distortion, and you were the designer, and you designed it to be okay at 20% distortion, and it wasn't going to be okay at 21% distortion. Let's think about what that means. Fundamental current of 100 amps. Harmonic distortion, 20 amps. That's 20% distortion. The total RMS current is 102 amps. So you designed your system to work at 100 amps, but not at 102 amps? Probably not a problem, okay? Most of the issues with harmonics, if they're heating, it's excessive harmonic distortion. And again, it's self-infecting. I'm usually screwing up my own system, so the utility doesn't really care about it. If it's above 20%, you start to get into some issues. But if you're designing a system that's above that, you have to really worry about, what is that doing to my voltage? And that's really, the concerns come into play where I'm screwing up my voltage enough to cause other issues. So now I'll talk about just, again, I'm going to fly through a couple of these because they're all in the paper and they go into some detailed descriptions about these. But really I'm going to talk about individual load solutions versus system solutions. So in some cases it makes sense to do the load solution, in some sense it makes sense to do the system solution. A line reactor with a VFD or a DC choke. Has anybody used those before? Line reactors? Okay. So they're like probably $3 to $5 per horsepower with a drive. It'll cut your harmonics in half, meaning if I don't have a DC choke or a line reactor, my current distortion could be 80%. If I do, it could be 40%. I've reduced my harmonic current. So remember what happens? Current flows out and flows back. If I stop it from flowing, it doesn't go anywhere. It's constricting it, doesn't allow it to flow. It's like grabbing a hose and squeezing it really tight so the water doesn't come out of it. Okay? There's a good video on that talks about what a line reactor DC choke is. The advantage are it's very inexpensive compared to other things. I wouldn't even suggest buying a drive that doesn't have a DC choke or AC line reactor. It would be difficult for me to understand putting money in after the fact, especially with drives. Here's what the waveforms look like. So it's very discontinuous current as opposed to that. And look at for example, just this one's 70%. So if this was 100 amps, that's 70 amps. And this one's like less than 40. So it makes a big difference just by having that DC choke or line reactor. You get kind of diminishing returns. So as you go up in, the bigger the percent line reactor, the less benefit you get out of it. Let me ask you this. This is a very sometimes confusing point. If I put a 10% line reactor in front of my drive, am I going to get 10% voltage drop? A lot of people think you do. The answer is no, you don't. We have a frequently asked questions video on that, and it's probably about 2 to 3% voltage drop. Because people say, oh, I put too much line reactor on, then I get a big voltage drop. What's the first thing a drive does with your voltage when you bring it in? 60 hertz voltage, then it does what? It rectifies it. It goes from AC to DC. So if I have a little bit of a flat top, if I have a little bit of a voltage drop, it's not a big deal. I'd much rather have a more impedance source than a less impedance source, as long as I don't screw up my voltage so much on that side of the system that I have other issues. But downstream of the line reactor, your drive's going to be okay. Here's where the DC choke would go inside the drive. The nice thing about a DC choke is you can put a bigger DC choke in a drive than the AC line reactor as far as the impedance goes. Physically, it'll fit more. So you can get a 5% DC choke in the same amount of physical space you get a 3% AC line reactor. What about drive isolation transformers? Does anybody use drive isolation transformers? Okay. So some of the benefits of that are you get true electrical isolation, but in fact, it also acts like a DC or an AC line reactor as well. So here's without the reactor. This has a a DC choke or an AC line reactor in the drive, by the way. That's why it looks a little different than the one I showed you before. But we're going from 50% down to, 33%. So 58% down to 33%. And you can see in the wave shape, it looks more what we'll call linear, more sinusoidal, okay? How about a drive dedicated filter? This is where that 10% line reactor comes in. Has anybody ever used a drive dedicated filter? What that means is I put a filter in front of each drive, and it makes it look from a 6 pulse to maybe an 18 pulse drive, okay? Much better. There's a 10% reactor here, then there's a shunt filter here, and we'll talk about shunt filters, but basically what happens is the harmonics come out of the drive, remember, and they look, and currents look, and they go, oh, the other thing that they told us wrong in college is current flows to the path of least resistance. That's wrong. What should they have told us? It divides according to the resistance, right? It flows to all paths, but it divides according to the resistance. So if this is a really high resistance or impedance, and this is a really low impedance, most of it will go here, and some of it might still go there. If this was equal to this, half of it goes there and half of it goes there, okay? But that's what a drive dedicated filter. What's the disadvantage of that? You're putting one on every single drive. So if you have a water treatment plant and you have 10 drives, but 5 of them are redundant, you put filters on every single drive when you really only need it on 5. So you might do more of a system level approach. How about a 12 pulse drive? This is with phase shifting. I can make a 6 pulse drive look like a 12 pulse. So you can do, you get less distortion, it looks more linear, okay? And then 24 pulse is what you end up with, especially with medium voltage. Anybody use a medium voltage drives? So yeah, so down at our experience center down in Houston, we have a sync transfer set up with a medium voltage drive, and we can show you the how that works. But we can show also the 24 pulse, which almost looks perfectly linear, okay? Now as far as, let's say, you go to the next step, you say, I don't want to do a single drive approach. I want to do more of a system, an individual load approach, but I want to do it on the load itself. I want to pay for that EV charger that's going to have lower distortion, or I want to pay for that drive that has lower distortion. So you can do things like computer power supplies that are lower distortion. They call them power factor corrected, but they're really lower harmonic distortion. You could get low harmonic distortion rectifiers or active front end devices. So this is what computer power supplies used to look like. This is what the power factor corrected ones look like today. At one point, these were $12 and these were $75. They've come together a lot more in cost, okay? But again, this is a lot more what the front end of a vehicle charger looks like. So how does a standard drive converter work? We convert from AC to DC with a diode bridge here, DC bus, and then we have an IGBT on the output, IGBT bridge on the output that converts from DC back to AC, and that allows us to change the frequency. The point of changing the frequency there is so that we can regulate the speed of the motor, okay? On an active front-end drive, or on a active front-end UPS, frankly, you could put a pulse width modulated filter here, which is basically like this thing in reverse. Put it over here. So in some cases, that could even double the cost of the drive. But you could argue that it can give you really nice, clean waveforms coming out of the drive, pushing back onto the system. When we do this with UPSs, by the way, we took out a transformer and a harmonic filter and put in an active front end. When we do it with drives, we didn't take anything out, we just add in extra stuff. So that's why, again, when you look at it, the difference between doing that on a drive and doing it on a UPS, it adds more cost. So here's what an active front end UPS or drive might look like in terms of current and voltage. And again, it's a lot more clean. Now, from a system solution standpoint, we could do these different things: tune filters, phase shifting, active filters, third harmonic filters specifically, or, and this is one that a lot of people have done for years, just oversize the equipment. If it's causing heating with a smaller piece of equipment, you put a bigger piece of equipment in, and it does a nice job of not heating it up. If I took a 75 kVA transformer, and this was the standard, we'll call it K1 transformer, a K13 transformer might be this big. And in fact, if you look inside and you kind of really scrutinize it, it may be 1.5 12 kVA transformer with a 75 kVA labeled. It's perfectly capable of handling 75 at 100% distortion, but it's just derated to do that, right? So that's how you oversize equipment. We talked about generators, why we do that. We do that to really reduce the impedance, okay? So let's talk about a couple of those. This is the shunt filter, and what happens is, remember, this changes with frequency. So 2 pi f times the inductance. Inductor, the impedance goes up. What happens with a capacitor? It's 1 over 2 pi f times the capacitance, so it goes down. So as they cross at a certain frequency. And this is, just to really stretch your mind this afternoon, this is, let's say, J10 ohms. This is minus J10 ohms. What's J10 minus J10? 0. So at some frequency, the current coming out of here sees 0 ohms and it wants to go that way and go back to the load. And then it never goes back on the system, hitting the impedance and screwing up our voltage, okay? That's how a harmonic filter works. So if you have harmonics coming out of each drive here, it will divide according to the impedance. Not all current doesn't flow to the path of least impedance. All current divides according to the impedance. And this is where some of it's going to go here, some of it's going to go there. If it doesn't all go through the impedance of the transformer, it doesn't screw up our voltage. We clean up our voltage and we clean up our system. We have a really good video on this one, and it talks about how the phase shifting works. But basically, you take 2 transformers here, delta delta or delta zigzag and delta Y, and these transformers make the wave shapes look a little different. They add together and become 12 poles. It makes a big difference. If you were designing commercial buildings and you shifted from, let's say, when we say we have, 3 floors here and you got a bunch of computer rooms, 5 rooms, 4 rooms, 3 rooms. Let's say you have fifth harmonic of each on each floor. So you have 5 plus 3 plus 4, 12 units of harmonic current, okay? If I do phase shifting on one of those floors, this one, I do a minus 3 there. So I have 5 plus 4, 9, minus 3 is 6. I've cut my harmonics in half just by changing one of my transformers. If I pick this transformer, I get minus 5 plus 4 plus 3. I get 2 units of harmonics, meaning if this was 120 amps of fifth harmonic current, now I'm down to 20 amps of fifth harmonic current. So it's this cancellation of harmonic current just by doing phase shifting. And that's, if I will tell you one thing, if you're designing, water treatment plants or if you're designing commercial buildings, take advantage of phase shifting. It's one of the easiest things to do because a lot of times you have to put transformers in anyway. Active harmonic filters basically are going to be just like the noise cancellation on your phone, right? How does that work? If I'm in a really noisy room, I'm talking to my phone, people don't hear outside of the room what's going on. They only hear my voice. And what happens is it injects equal and opposite frequencies. Or like if you have noise canceling headset, it injects equal and opposite frequencies. So it injects this garbage to add to that to make it look nice. Again, that's what's drawn from the source or pushed back to the source, okay? We talked a little bit about third harmonics adding up on the neutral. Just briefly, they can do, this isn't as big of a problem anymore because they have a lot of the better power supplies. Putting in a different transformer to handle those harmonics, for third harmonics, like this, a delta Y, or like this, a delta zigzag, we can make it a little bit more efficient. I want to skip ahead sort of more towards the end here. I want to show you a couple of things at the end. So resonance is a really important issue. You guys ever see the Tacoma Narrows Bridge? It oscillated and it ripped itself apart. If you put capacitors on a power system, basically they will resonate at a certain frequency. And in this case, if they resonated around the 7th harmonic and I have a 6-pulse drive, do I have a source of 7th harmonic? Yeah. So I'm pushing 7th harmonic out, and let's say I push out 10 amps of 7th harmonic current. Between these two things resonating, it may get up to 1,000 amps of 7th harmonic current. What's going to happen? Hopefully I blow my fuses. Second, I might blow my capacitors. Third, I might blow up my transformer. Resonance is not a fun thing to deal with, okay? So as you add capacitors onto power systems that have harmonics, and we know harmonics are the new normal, you have to deal with it. So again, you don't want to see that, right? There's an example again of heating. If you get a transformer and it causes a lot of heating, we can have issues with that, right? You can actually have voltage distortion from nonlinear loads cause linear motors to essentially want to spin backwards, which is not good either. It's like driving with your foot all the way to the floor on the gas pedal and pumping your brakes. Not very good idea. That's kind of what happens electrically. And then one last thing here, and then I'll show you the video page, is if I take my power triangle, kilowatts, kVAR, kVA, if you look at your power factor displacement, your power factor, just 60 hertz, that's what it looks like. As I add in harmonics, it's almost like I'm adding a third dimension to that power triangle, and essentially end up with more kVA. And so when I take kilowatts divided by kVA, my power factor is always going to be lower if I have harmonics, okay? That's my total power factor. So this is the last page. Basically, we have a whole bunch of videos on our eaton.com/experience website and under power quality specifically. And then we have 49 frequently asked question videos. There's also just eaton.com/harmonics. You guys will get a copy of this presentation. There's actually 120 slides in here. I hit a bunch of them, so you guys wouldn't have to, I wouldn't have to go really fast. I already went kind of fast, but anyway, that's it. So if you're in any of those situations and you want to figure out harmonics, I mean, it's important. It's the new normal, but you got to deal with it in the right way. And sometimes doing nothing is the right thing, right? Okay. I'll stick around for questions or if anybody has anything quick. But I know we want to try to take a break here.
10-minute break. So about 3:10, we'll start into energy transition, and we really want to make that presentation kind of a engaging conversation when we get to it.
Yeah, question.
So you mentioned in the start that you tested a bunch of EVs.
Yeah.
Which one performed the best?
So the question was, we tested a bunch of EVs, which one performed the best? Tesla did a really good job, and there's several other ones that are very similar to that. I think the new Lightning was pretty good. There was a couple that were kind of pushing that 8 or 9%. I don't remember specifically which ones they were, but I remember specifically like the Tesla one, because and I think they've been at it for longer than most of these people, so it's been pretty good.
Way off? Is Tesla much better? Or?
No, I mean, it would go from, say, 4% distortion. So on a 100 amp basis, they had 4 amps of harmonics, and the other ones had 8 amps. So it's almost like if you look at the waveform and you didn't have a meter that could measure it, you would think they're the same. You know, it's very close, very close. Yeah.
Just on isolation transfer, where would you say is the ideal application for a situation?
So the question is, if you, on an isolation transformer, what's the ideal situation for isolation transformers with harmonics? And it's really all about, if you can use them for phase shifting, that's going to be your best bet, because now you're canceling some of the harmonics from other loads, as opposed to using it just for the impedance, like a line reactor. Because a line reactor would be like $3 or $4 a horsepower kVA. Isolation's $50 a kVA roughly, or whatever. But if you can use it for phase shifting, 100%, it's a much better solution. Yeah.
So if I have an unreliable source, that would be a good.
Yeah, you don't know what you're getting from. Yeah, exactly. Yeah, absolutely.
So if I want to improve the power factors for the system, you say if I add the capacitor, I need to watch out for the
Yeah, so if you're adding capacitors with when you have harmonic sources, so you have a source of harmonics. The Tacoma Narrows Bridge failed because the wind was blowing, but if the wind didn't blow, the bridge would have been fine. What happened was the bridge started to make it move, okay? So if you don't have harmonic currents, then the voltage, or then the current distortion wouldn't get amplified. So you can have a resonant point when you put a capacitor on, but when you excite that resonant at the frequency of interest, which is what harmonics are, 300 hertz, 420 hertz, before you only had 60 hertz. The resonant point was over there somewhere. Now you have this resonant point. So we have a couple good videos on that one as well. It's, you know, and I can give you my card if you have other questions on it, but it's definitely worth looking into.
Yeah, so how do we correct it? We have both of them.
So when you correct it, the best way to correct resonance is to apply either a harmonic filter to tune it to where you know exactly where it's going to be, or to get rid of the harmonics. Sometimes it's harder to get rid of the harmonics from the load or the source. Yeah.